or the basal nuclei. Ultimately, we're going to transition to the limbic system. I believe your final exam has been scheduled for Friday the 18th. It will not be Friday the 18th for a lot of good reasons. Mostly because I'll be on the other coast of the United States by then. Just like students do. I made all my flight arrangements based on what should have been the schedule. So we'll probably just slow down a little bit, get everything wrapped up, and have the last exam, the last day of class. Okay, and you'll be done.
When is it? The 16th? The last day of class?
Last day of class.
16th is the Wednesday.
No, 16th is finals week. 16, 15, 14. It's the
14th is Monday.
It's the fourth. It's what?
14th.
It's the 14th. All right, so it's the Monday the 14th. Yeah, yeah. It's well. The reason is this is the most screwed up semester I've ever seen. It's a week short, and all the labs are screwed up. You haven't been told yet, but there was a screw up with labs, right? Even for this class, so you won't do the endocrine lab stuff. And yeah, it's just crazy. And then they moved exams to the Friday. And exams, believe me, I have students that are complaining that they have exams starting at 7:30 in the morning some days, and it's completely out of our hands. So, the basal ganglia. These are really important midbrain structures that are involved with the majority of movement pathways that we see. We're going to look at the anatomy of this whole area, but then we're going to be looking at pathways. The pathways that come through here are critical to know and understand because so many movement disorders involve these pathways in one way or another. Inhibition and excitation become really critically important here because just like the cerebellum, you remember in the cerebellum, all of the outputs from the cerebellum are inhibitory. And the control on the amount of inhibition comes through interactions within. Same thing with the basal nuclei. All of the outputs coming from the basal nuclei to other structures are inhibitory. And it's the inhibition of those inhibitory pathways that becomes critically important. So we'll be looking at that. We'll be talking a little bit more about neurotransmitters. Understanding how neurotransmitters work and understanding receptors. What you're going to see by the end of the day today is that for some neurotransmitters and some pathways, there are so many different subtypes of receptors that it becomes problematic with dealing with neurological problems. The various channels that go through here are on the surface a little bit complicated, but once you understand them, they become a little less complicated. And finally, we're going to be looking at a number of movement disorders that involve many structures within this and associated with it. So here we have this lateral view that shows you part of the basal nuclear complex. We have the putamen sitting here. We've got the caudate nucleus, which is big and odd-shaped. We've got nucleus accumbens sitting here. We've got the amygdala. And sitting behind it, you'll notice the lateral ventricle. It's a very good landmark, just to give you an idea of where it sits. The organization here, nomenclature-wise, is confusing. Globus globus pallidus, subthalamic nucleus, and substantia nigra. You didn't see any of those in that previous illustration because those sit slightly internally to the external structures. But there are two other sets of names that are commonly used in association with the basal ganglia. One is the lenticular nucleus, which is the putamen and the globus pallidus together. That was a structure that was described a long time ago. The other is the striatum, which is the caudate nucleus in the putamen. It's just really important to remember these relationships for the simple reason that you will see reference to the striatum repeatedly. We've already seen it where we've talked about outputs from certain areas that go to the striatum. That's referring very, very specifically to the caudate nucleus and the putamen. When we look at the kind of medial view here, so here we have nucleus accumbens, here we have the caudate nucleus coming down to the amygdala, sitting there we have the putamen. Internal to that, and here we have the thalamus. So we have two thalami sitting there like this, your left and your right thalamus. Sitting to the outside of that, we have the two sets of basal ganglia. And then here we have globus pallidus. Still, even in here, they're not showing you all of the structures. It's really hard to show everything in there.
So we got, sorry, so you have two thalami and then you have the
So-
basal ganglia, like two basal ganglia sitting internal or?
So here we have the two thalami, all right? And then sitting out here, we have substantia nigra, subthalamic nucleus, and we have the globus pallidus and the caudate sitting, the putamen. We don't even see the caudate very well in this pathetic sketch. All right? So we could say this is the midline to the brain. Once again, being able to navigate using the thalamus as a landmark becomes really important. We're going to look at that in pretty good detail in just a few minutes. Nucleus accumbens gets a little bit of a short description in your textbook, and it's a scattered description. So I tried to pull it all together here. Inputs to the nucleus accumbens comes from association cortices, the amygdala, and those mesolimbic pathways. We talked about the mesolimbic pathways the other day when we were talking about all of those reticular formation pathways. Outputs go to the substantia nigra, go to the ventral globus pallidus, from there to the thalamus and the prefrontal cortex. So let's think about this. With nucleus accumbens, all of the different association cortices are sending signaling here. And then those signals go out to the prefrontal cortex. What it manages to do here is get a tremendous amount of information on position, on all sorts of sensory inputs, and use those to help determine, in part, how some movement is going to take place. But that prefrontal cortex is involved with so much stuff. It's involved with movement and movement planning. It's involved with executive management of many, many behaviors. The neurotransmitters associated with nucleus accumbens, dopamine and serotonin. dopamine and serotonin are without question the two neurotransmitters that are intimately associated with reward pathways. Dopamine and serotonin levels basically control how you respond to rewards, how you acknowledge rewards, how you understand the reward system. As a result, these two pathways are very sensitive to endorphins and to opiates. Those opiates can be your endogenous opiates, but those opiates can just as well be, street drugs or morphine. So there's a lot that goes on here. So we have your basal ganglia sitting there, part of the striatum, the thalamus, the lateral ventricle, all of these structures. Now, to understand how signaling works in this system, you have to review again the concepts of inhibition and excitation. I know we've done that a couple of times this semester, and I'm trying to just once again give you a slide that covers the basics of what's going on. We're going to be visiting all of these neurotransmitters in the next hour. Inhibitory, GABA and Keflin, substance P. Excitatory, glutamate and acetylcholine. And either excitatory or inhibitory, dopamine. This is critical to understand. These are all neurotransmitters that affect how you behave. So there's a lot of behavioral issues going on here and behavioral motor issues. We tend to think of the basal ganglia as being intimately involved with movement, but they're intimately involved with a couple of other functions as well. Now, with all of these neurotransmitters, with the synapse, we have a lot of issues. So here is a typical synapse. And the question is, in any behavior that you exhibit, how do we get the signal from here to here, number one? Number two, if there is a problem getting the signal from here to here, what's the problem? And I attempted to summarize it for you. It is obnoxiously difficult to figure out what the problem is getting a signal along a signaling pathway. Is it the production of the neurotransmitter? Are you producing enough neurotransmitter in the cell body, at the nucleus, at the mitochondria, the endoplasmic reticulum in here, to do what you need to do? The movement of the synaptic vesicles. These vesicles move along some fiber pathways, protein pathways within the axon. Are there problems with those? Were those made incorrectly? Do you have an inappropriate chemistry for them to move? The release of the synaptic vesicle into the synapse. So far we have three ways to affect getting the signal. Binding of the neurotransmitter. So the neurotransmitter has to bind at the target. Are there enough receptors? Are there too many receptors? Are there too few receptors? All of that affects the signal. Reuptake of the neurotransmitter. You release neurotransmitter here, but ultimately excess neurotransmitter is going to be taken back into the synaptic terminus. That can happen either from directly at the terminus, or it can diffuse